So if you haven't seen it already, I'll give you guys some time to like, look at it and think about it, and then we'll be going over it shortly.
Feel free to type in the chat if you have any ideas.
Okay, so if you guys have ideas, you can like feel free to like put them in the chat, and yeah. Okay, so I guess we'll go over the question now. So I guess one thing to like, I think that you see first when you're looking at this question is that like you basically have this tetrahedron whose like base is an equilateral triangle, and then you have a point D that's directly above its center, essentially, right? So then what this tells you is, well, basically you have a lot of equilateral triangles if you take some horizontal cross sections, right? So like we'll take a horizontal cross section in particular. We know that like E, F, and G, since it's like symmetric about like between A, B, and C, E, F, and G are all therefore going to be on the same plane parallel to A, B, C, right? So then we suppose that we take this plane and we intersect them with segments DA, DB, and DC, right? So, well, we call these points X, Y, and Z. And now we consider like how X, Y, Z, E, F, and G relate to each other. Right? Well, basically, we see that, well, because we're going to take advantage of the symmetry again, EF and G have to lie on the lines of symmetry of the three isosceles triangle faces, right? Um, because this problem is symmetric in that way, so then they lie on that line of symmetry. Well, this tells us that they lie on the midpoints of the triangle X, Y, and Z, X, Y, Z, right? Because because X, Y, and Z are going to be on the two edges of the isosceles triangle, or the three edges, and then so the midpoint is going to be E, F, and G, right? So, well, this tells us in particular that EFG has 1/4 the area of XYZ because it has half the side length, right? So, well, that's good, nice information to know. Well, now, but we still don't know much about like the side lengths of XYZ, right? So let's just suppose that the side length of XYZ is K, where the side length of ABC is 1, right? So then you have, it's basically just the ratio of the side lengths, right? So, well, we basically want to try to find the ratio of the volumes in terms of K, right? So, well, we know that the ratio of their bases is going to be, the ratio of the areas of their bases is going to be K squared over 4, right? Because XYZ had the ratio of the areas of XYZ to ABC is going to be K squared. And then EFG is 1/4 of XYZ. So then it will be K squared over 4. Right, so, but now we also have to find the height, which is a bit more tricky to see. Right, so basically, we consider this, it's like a pyramid inside of a pyramid, right? And well, basically we think about, so we see that essentially this plane EFG, this cuts the pyramid ABCD into a smaller similar pyramid DEFG on top, and then something on the bottom. Right, so well, we consider just the ratio, the sums of the heights of everything. Right, well, so the ratio of the height of DEFG to DABC is going to be, again, K, because they're similar. And then the ratio of, and then so that leaves 1 minus K of the height to be the height of everything else, which also happens to be the height of EFGH. So what this tells us is we now have an expression in terms of K that we want to maximize, right? And then now from here it's just algebra, right? We can use AIME on this expression, for instance. And then we can basically just see that the maximum that it attains is when K equals 1/3 and when K equals 2/3. And so that is 1/27. So our answer is 28. Right, so are there questions on that one? If not, we'll move on to this week's topic, which is advanced geometry.
Yeah, so the first topic that we're going to be covering today is angle chasing. So in angle chasing, there's a few important results that we should probably discuss before we start the problems. So you might have seen these before. So the first one is the inscribed angle theorem. And that says if you have some ABC in the circle as shown in the diagram, then and O is the center of the circle, then angle AOB is twice angle ACB. And also if you have another point D that subtends the same arc, you have ACB equals ADB. So to show this, we basically just use the properties of a circle. So OA equals OC and OC equals OB. So we have isosceles triangles there. So if we let angle ACO be alpha and angle BCO be beta, then we also know that angle OAC is also alpha. So then since the sum of the angles in the triangle is 180, we have angle AOC is 180 minus 2 alpha. So that's like this angle here. And similarly, if we said angle BCO is beta, then also angle OBC is also beta because OB equals OC. So then we have that angle BOC is 180 minus 2 beta because, again, the sum of the angles in a triangle is 180. And so now at this point O, all three of these angles, AOC, BOC, and AOB, all add up to 360. So that means that AOB is 360 minus AOC minus BOC. And if we evaluate that in terms of alpha and beta, we just get 2 times alpha plus beta. And remember that alpha and beta have to add up to angle ACB. So we get angle AOB is 2 times angle ACB. And so for the second part of this, angle ACB equals angle ADB, this is just true because if you notice here that angle ACB is actually independent of the position of C, because angle ACB is equal to 1/2 times angle AOB. So since it's independent, it doesn't matter where the point C is. So if C was over here, then we still have the same angle. And alternatively, both of these angles are equal to 1/2 angle AOB. So that's the inscribed angle. And so now another important result is cyclic quadrilaterals. So if ABCD is the convex quadrilateral, we say that it's cyclic if all four points lie on some circle. So the main claim is that these three conditions are equivalent. So being cyclic is equivalent to opposite angles adding up to 180 degrees, and also angle ABD equals angle ACD. So this third number here, angle ABD and angle ACD, notice that they both subtend the same arc AD. So this is actually basically the result of the inscribed angle theorem. And the second bullet is actually because angle ABC from the inscribed angles theorem is 1/2 of this arc AC, but angle CDA is 1/2 of this arc AC. And since both of these arcs compose the whole circle, this is just 1/2. When you add these two angles, you just get 1/2 times the number of degrees in a circle. So you just get 360 over 2, or 180. So So yeah, so both 2 and 3 are basically saying the same thing. And so in like the resulting problems, we'll probably be using cyclic quadrilaterals to deduce like other angle relationships, maybe similar triangles, etc. So with that, I guess we'll start with the first angle chasing problem, and Brian will do that.
All right, so here's the next angle chasing problem. I'll give you guys some time to think about it, and then you can send ideas in the chat, and then we'll be going over it later. All right, so I guess we'll go over it now. So I guess like a thing to note is that like we want to find a bunch of equal angles so then we can eventually use those equal angles to do something else, right? This is a lot of what you do in angle chasing is you find equal angles and then use those equal angles to do other things, right? So, well, what can we use in this problem? Right, well, for example, in this problem, you're given parallel lines, right? AE is parallel to BD here, right? So we want to somehow use this to help us angle chase, right? So, well, for example, you have that DEY, the angle DEY equals angle CDB, right? Because BD is parallel to AE, right? And then and then now you see that CDB and CAB share the same arc, so they must be equal as well. right? So we got this pair, we got these equal angles, right? And we also see that AYD and ABD are EYD and ABD are equal, right? Because EYD is 180 minus AYD, which is 180 minus ABD. Right. So well, what does this give us? Right. Well, we have a bunch of equal angles now. And then, but we see that these equal angles are actually like in the same two triangles. In particular, we see that like in triangles DEY and XAB, we have two of the angles are already equal. Right, so we have DEY is similar to XAB. Right, because yeah. So we have these two similar triangles, right? So well, now what? Well, basically, we remember that we want to find the area of DEY. Right, so how would we go about doing that? So we don't exactly have AB equals ED because like it might look like AB and CD are parallel. They're not actually parallel. So like that's not a parallelogram, right? So you can't do that, right? But you're on the right track, right? Because what we do have two equal sides, but like they're not AB and DE, right? So like what are they? It's not AB and DC either. You don't have enough information about those to say anything about that, right? But like, remember that like you still have these parallel lines, and then they're intersecting the circle, right? And you used it once, but like you could still use it again, right? So yeah, exactly. AB and YD, right? So because AB equals YD because we have essentially a trapezoid that's also cyclic. And there's only one way for that to happen, and that's for it to be an isosceles trapezoid. Right, so yeah, we have that AB equals YD. Or DY, sure. Yeah. So that's useful, right? Now what? Now what do we do? remember that our goal is to eventually find the area of DEY, right? So like in this problem, we have that DEY is somewhat distant from everything else, right? But we want to like it's especially distant from a lot of the lengths that we're given, right? So well, we want to somehow bring it closer to the lengths that we're given, right? So how do we go about doing that? In particular, we have that DEY is similar to XAB, right? Exactly. Well, yeah, you want to use the fact that they're similar to do stuff, right? And well, like using those lengths isn't even necessary in this case, right? Because we can go even further than that. We can just find the area of DEY directly with the similar triangles, right? All we need is the ratio of the triangles, and then we'll be able to find the area, right? Because we remember that in triangle AXB, we already know everything. We're given all three sides, so then we can calculate it exactly. Right, and then, so then calculating any other side lengths of DEY isn't actually necessary because since we already have one of the side lengths of DEY, that's enough to just determine the ratio. And now it's just, to finish, we just solve for the area of DEY in that equation. Right, and then we get that the answer is 400 over 21. So then that's our answer. Right, so does anyone have any questions about that? If not, I guess we can move on to the next question. And so this is the next question, and I'll give you guys some time to think about it. And if you have ideas, you can send them in chat, and then we'll be going over it. Okay, so what ideas do people have for this problem? So I think so. Something that you would do when you're starting out this problem is you would just find a bunch of equal angles and see what you can do with them. Right. So let's try that. So well, we see that we have these circles, and we want to somehow be able to take advantage of them. Right. So we have a bunch. So the circles always give us equal angles, right? Because if the circles have 4 points on them, then it forms a cyclic quad, right? And then we already learned some of the properties of cyclic quads, right? So we want to somehow use those properties, right? So like what angles can we say are equal to each other? So like we want to somehow take advantage of circles, and remember we want to like basically angle chase, right? But so also so basically we see that we have these circles, and then so for example we can have something like angle ACF equals angle ADF, right? Because they both subtend the same arc. And we also similarly have angle BCF equals angle BEF because they also subtend the same arc. Right, so well, what happens if we subtract these two? Right, so like we have these two equations, and then like basically we want to do something with them. So then what does that give, like when we subtract these two equations? So it tells us that, so ACF minus BCF we can find is angle, we can see is angle ACB, right? So that's the left side. And then what's ADF minus BEF? Right. Well, you see that angle ADF is the exterior angle of triangle DEF, right? So then it's the sum of the two other interior angles. But one of those interior angles was BEF. So then their difference is the other interior angle, which is DFE. So we now have this nice fact, which is angle ACB equals angle DFE. Right, so what can we do with this fact though? Like, We want to somehow be able to use it, right? So what do we do with it? Exactly. We can use the law of cosines, right? So I didn't show the calculation here, but you can just use the law of cosines on angle C and triangle ACB, and then you can find that the cosine of angle ACB equals 3/4. Right. So, well, this is nice, because we remember that like this also tells us that the cosine of DFE is 3/4. Right. So, well, what can we do with that? Right. Exactly. We can plug in DF and EF. So we plug in DF and EF, and then that tells us that we can calculate DE. Right. So we can calculate DE, and we can find DE is 4√2. Right. So we now have DE. Right. But now what? Right. So like, what can we do from here? I think someone mentioned it earlier. Right. Which was, yeah, you have similar triangles. Right. So we're going to let X be the intersection of AE and CF, so then we can take advantage of the similar triangles. Right. But basically we now just get a lot of similar triangles. Right. I think it was already said that like I think ACX is similar to FDX, or you can also say it like that, right? And you also have FXE is similar to BXC, right? But we see that in particular, this tells us that we can calculate FX in two different ways using the two different pairs of similar triangles. Right. So if we let X equal BX and Y equal DX, right? We can write equations, and then this is good. So if we just plug in the values that we know into that bottom equation, right? What does that give, right? That gives us, so we have like AX is X plus 4, FD is 2, and then AC is 6, and BX is X, EF is 7, and BC is 5. Right, so we can plug in all those values and we can get this nice equation in terms of X. So then we can solve for X, and then we can get X is 5/4. Right, so if X is 5/4, we still haven't found Y yet, right? Because we want to find Y so then we can find the total BE, right? So how do we find Y now? Yeah. We could use the similar triangles again, essentially, right? So that not the solution I have. It does work. It's basically you do whatever you just did for x with y again, and then you get another equation and stuff. So it does work, but I'm going to do it a slightly different way, which is to use power of a point, right? So power of a point is actually just similar triangles, right? So it is basically the same thing, but yeah, but you get slightly different equations. But this is just nicer equations in this case because you deal with a root 2 less often. But yeah, you can get an equation like this, where basically you see that cx times fx is equal to both ax times dx and bx times ex. And then you can calculate both of those in terms of x and y. And then you simplify this equation to solve for y, right? And you can get that y is root 2x, which tells us that it's 5 root 2 over 4, because we already found that x was 5 over 4, right? So, well, now from here it's just, we already found all the values that we need, right? Because we look at b is bx plus vx plus de, and we already found all three of those values, right? We have that x plus y plus 4 root 2. And then so that gives us the answer of 5 plus 21 root 2 all over 4. And then so we add up all the things that we have to add up, and then we get that the answer is 32. All right. So does anyone have any questions on that one? If not, I guess we'll move on to the next question.
All right, so let's get started. So does anyone see any types of angle relationships that we can use here? Just say it in the chat. Yeah, exactly. So because AC is tangent to omega 1, we have that angle ABK equals angle KAC because they both subtend the same arc. And similarly, because AB is tangent to omega 2, we have KAB equals ACK. And now because we have both ABK and um, ABK and CAK have two equal angles. They both are similar. So we have BKA is similar to AKC. So from this, if we let AK be equal to X, then we can actually find out some of the other lengths in terms of X. So because of the similar triangles, we can say that we can first find the ratio between the two triangles. So the ratio of the two triangles is AB over AC, which is 7/9. So if we were to let AK be X, we know from the similar triangles that AK over KC is 7/9 because they are corresponding sides in the triangles. So that means that KC is 9/7 X. So from this, like similarly, we could also say instead that BK is 7/9 X. But from this, does anyone see any way to get the value of X? So note that we have AK and KC both in terms of X. Yeah, so we have like three of these sides of this triangle, but two of them are in terms of X. So if we had like one of the cosines of the angles, we could apply the law of cosines and solve for the value of X. So that's like our main motivation here. So we are going to look at angle AKC and try to find out what it is in terms of angles A, B, and C. So angle AKC is 180 minus angle KAC minus angle KCA. And because of the similar triangles, we said that KCA is equal to BAK. So then this is 180 minus KAC minus BAK, but KAC plus BAK this is just angle A. So this simplifies to 180 minus angle A. So now this is pretty useful because we can say that cosine of angle AKC is negative of cosine A. And we have all of the side lengths of AB and C, of ABC, so we can actually just determine what cosine of A is. So cosine of A is 7 squared plus 9 squared minus 8 squared over 2 times 7 times 9. So we get 11/21. So that means that cosine of AKC is negative 11/21. And now we just apply the law of cosines to triangle AKC. So we get x squared plus 81/49 x squared plus 2x times 9/7 x times 11/21 equals 81. And here the whole left side simplifies to 4x squared. So we can solve for x. So we get x is 9/2. And our final answer is 11. So does anyone have any questions on this? Okay, so I guess we'll move on to our last angle chasing problem before the break. Okay, so let's get started. Does anyone have any ideas for how to compute the area of BPC or anything about triangle BPC? Okay, so if there's no ideas, I guess I will just say. So I've drawn two of the cyclic quadrilaterals that we know here. So B I sub B dp and C I sub C dp. So we really don't know much about triangle BPC, but because of these cyclic quadrilaterals, we can try to determine some of the angles. So if we look at the angles of triangle BPC, we notice that angle BPC can be broken down into angle BPD and angle CPD. So we're looking at angle BPC, and you can write BPC equals BPD plus angle CPD. And now from the cyclic quadrilaterals, we have BPD is 180 minus angle BI sub BD, and CPD is 180 minus angle CI sub CD. So from this, does anyone have any ideas for how to like evaluate these two angles now? So I think the key thing to remember here is I sub B is the incenter of ABD, and I sub C is the incenter of ACD. So maybe if you don't see it right away, let's just say you have some triangle like XYZ and it has an incenter I. Like we basically just want to find the angle YIZ. So like the only thing we really know about the angles is that there's like angle bisectors. So from that, can anyone say like what one of these angles is? Yeah, exactly. So we have BIBD is 180 degrees minus DBIB and minus BD I sub B. And like, since it's the incenter, this is 180 minus 1/2 angle B minus 1/2 angle ADB. And since the three angles in a triangle add up to 180, we have angle B plus angle ADB plus angle BAD is 180. So if we multiply that by 1/2 and subtract, we would get that this is equal to 90 plus 1/2 times angle BAD. So this is like a pretty general fact about incenter. It's good to know. So if we do that for the other angle as well, we get that angle CI sub CD is 90 plus 1/2 angle CAD. And now if we plug this in and simplify, we get angle BPC is 180 degrees minus 1/2 angle BAD minus 1/2 angle CAD. So it's equal to, so since BAD and CAD add up to angle A, this is 180 minus 1/2 angle A. And so since we know everything about, we know the side lengths of ABC, so we know angle A. So this means that the angle BPC is really fixed in this problem. So it seems useful to determine the angle A from this. So to determine the angle A, we'll just use the law of cosines. So cosine A is 10 squared plus 16 squared minus 14 squared over 2 times 10 times 16. So this comes out to 1/2. And that means that angle A is 60. And if we plug in our relation for BPC, we get BPC is 150 degrees. So we have that BPC is always going to be 150 degrees no matter where D is on BC. So BPC is fixed. So can anyone say what the locus of P is? So what's the set of points that P can lie on? Yeah, exactly. So it's not going to be the whole circle, but it's just going to be the arc of the circle. But so now this is so now that we have this, I'll just say that we know it's the arc of a circle because if if we have some arc with an angle measure of 300 degrees, and we have some point on that subtends that arc, it's always going to be equal to 150 degrees. So that's what we have here. And so since this BPC subtends an arc of 300 degrees, we can just find BOC. So O is the center of this circle. So BOC is 360 minus 300, or 60 degrees. So given that BOC is 60 degrees, and so this is a circle, so BO equals CO. So that means that it's an isosceles triangle with an angle of 60 degrees. So it's also an equilateral triangle. So yeah, BOC is equilateral. And so we know that BC is equal to 14. So that means that OB and OC are also equal to 14. So 14 is the radius of this circle. And so now we have a good idea of where P can lie, and we can return to the main problem, which was to find the area, maximum area of BPC. So does anyone have an idea of where that would be on this curve? Yeah, so this area, so we can write the area as base times height, and the base is always 14, so we just want to maximize the height. And the height is maximized at this midpoint of the minor arc BC. So the maximum height is just the radius of the circle minus the height of that equilateral triangle. So the radius of the circle is 14, and the height of the equilateral triangle is 7√3. So the maximum height of BPC is 14 minus 7√3. And then we just use 1/2 base times height to find the area. And so the area comes out to 98 minus 49√3. And the final answer is 150. So does anyone have any questions? Okay, so we'll have a 5-minute break, and we'll come back and we will do radical axes after that.
Called radical axis. So the radical axis has to do with power of a point. So I'd encourage you to draw your own diagram as we go through this, go through the definitions. So if you have a circle omega and a point P outside omega, then you can draw any line L through P. And suppose that our line L intersects omega at A and B. Power of a point tells us that PA times PB doesn't depend on L. Does everyone see why? If we have another line passing through P, then we can use power of a point to establish that PA times PB is equal for both lines. So this quantity doesn't depend on L. So let's try to find another way to express what PA times PB is, because right now it depends on a line that we don't have control over. So to set the diagram up, suppose that O is the center of omega and R is its radius. How else can we express the product PA times PB, which is independent of line L? Well, since it's independent of line L, we can choose what L is. So let's choose L to be line OP. With this choice of L, can anybody figure out what the product PA times PB is? It should be in terms of just OP and R. So given this choice of L, what is PA times PB? You should be able to work out that it's equal to OP squared minus R squared. And you can just do this by, because it ends up PA and PB are OP plus R and OP minus R in some order. So it works out to that. So for this calculation, we assume that P was outside omega. If P is inside omega, then the calculation is slightly different because the order of the points on the segment is different. And when P is inside omega, it's the negative. It should be R squared minus OP squared. So we see that this quantity, OP squared minus R squared, is pretty helpful because by power of a point, it is what PA times PB is for any choice of L. So we'll define OP squared minus R squared to be the power of P with respect to omega. And note that this quantity is actually negative if P is inside the circle. So this quantity encapsulates what PA times PB is going to be. It's equal to PA times PB if P is outside the circle, and it's equal to negative PA times PB if it's inside the circle. Does anyone need me to go over this slide again? If not, then we can move on to the slide 2 out of 3. If you have any questions, be sure to stop me. Next slide, please. So the radical axis arises from the question, if we have two circles, omega 1 and omega 2, what is the set of points that have the same power with respect to both circles? So that is, find all points P such that the power of P with respect to omega 1 is also equal to the power of P with respect to omega 2. So the answer ends up being a line. And this line we call the radical axis of the two circles. And the radical axis also happens to be perpendicular to the line joining the centers of the two circles. So if we let this, whoop, that was a little bit too far. Yep. This line is perpendicular to O1, O2, if we set O1 and O2 to be the centers of the two circles. So now we've made two clicks. The answer is a line, and this line is perpendicular to this line joining the centers. And you can prove this with a relatively clean use of coordinates. We have the full derivation in the handout, but just for time's sake, we're not going to go through it in class. And as mentioned earlier, if the two circles intersect, then the radical axis ends up being the common chord of the two circles. This is because each intersection has 0 power with respect to both circles. So each intersection point lies on the radical axis. And since the radical axis is a line, and we know 2 points on the line, we can just draw the common chord, which is the unique line containing both points. Are there any questions about this slide? If not, then let's move on to the third slide. So given our definition of radical axes, we can find a very useful theorem about the radical axes of 3 circles. And we call this the radical axis theorem. So the statement is as follows. If we have 3 circles and we draw the 3 radical axes of each pair, then these 3 radical axes are either concurrent or all parallel. The statement over there is a little more in detail. I'll give you a couple of seconds to read over it. So to prove that this theorem, the proof uses the equal power property of the radical axis. And it's much like the proof that the circumcenter exists or the incenter exists. So suppose that L1 and L2 intersect at a point P. Well, by definition, since P lies on L1, it has the same power with respect to omega 2 and omega 3. And since P lies on L2, P should have the same power with respect to omega 3 and omega 1. Now, we can use these equalities. P has the same power with respect to omega 1 and omega 2. And by definition, this means that P lies on the radical axis of omega 1 and omega 2, which is L3. So what this means is if any two of the radical axes intersect, then their intersection lies on the third radical axis. So if two of these radical axes intersect, then all three are concurrent. Otherwise, none of the radical axes can intersect, which means that the three radical axes have to be all parallel. And if the three lines are concurrent rather than all parallel, we call the concurrency point the radical center of the three circles. Any questions about the theorem or radical axes in general? If not, then this ends our exposition on radical axes and we can move on to our first problem. So the problem and diagram are as shown. So the diagram here is a clean diagram. I'd encourage you to also get a copy of the clean diagram so you can add points as needed. The diagram on the next page will be a complete diagram. So it might be a big jump. So let's move on to to working on this problem. So yep, a good observation is that CF is the radical axis of the two circles in the diagram. Unfortunately, this isn't super useful right now because the two circles don't intersect in a lot of nice points. There's not much we can say about the relationship between these two circles. So given that CF is the radical axis, it would be nice if we could use the radical axis theorem to find some more information about it. If we can get a third circle, then we can use the radical axis theorem to find another point on CF. So we're going to use the fact that the radical axis of two intersecting circles is their common chord. So the radical axis theorem in this case can be interpreted as the fact that the common chords of three circles concur. So in order to be able to use this common chord property, we're going to want this third circle to intersect ABC and CDE at nice points. Does anyone have any suggestions on what circles we could use? As a side note, it's not if the circle passes through C, then the information is useless because C will be the radical center of the three circles, and we already know C is on CF. Yep, well, the diagram here might give it away a little, but we can try AEB. So we're just motivated by choosing A and B on our first circle, and then choosing another point on the second circle. But with this circle, it's pretty nice because it seems like the second intersection of this circle and CDE is also nice. And if this fourth point is also nice, then we can get some simple facts about CF. So if you draw in ABE, it looks like that the second intersection of ABE and CDE is a nice point on BC. In particular, if we drop the perpendicular from A to BC, it looks like X is on both CDE and AEB. And it would be very convenient if this was true, because then the common chords are all nicely easy to get points. So let's try to prove it. Well, first, if we take a look at the diagram, we see that AEBX is a rectangle. That's because BX is parallel to AE from the parallelogram. AX is the perpendicular to both of them by definition. And BE is also perpendicular to both of them because we're given that. So that tells us that X is on the circumcircle of ABE. Now we're going to need to show that X is on the circumcircle of CDE. And to do that, we see that CX is parallel to DE, which means that CXED is a trapezoid. And a trapezoid is cyclic if and only if it's isosceles. So it's enough to show that it's isosceles, which will directly imply that it's cyclic. So we take a look at EX. And since a rectangle has equal diagonals, we know that EX is equal to AB. And since ABC is a parallelogram, we know that AB is equal to CD. That means EX is equal to CD. So the trapezoid is isosceles. That's good, because now we have this third circle which intersects the other two circles at nice points. So let's use the radical axis theorem on ABC, CDE, and AB. Well, the radical axis of ABC and CDE is CF. We've observed that earlier. The radical axis of AEB and ABC is AB. It's their common chord. And the radical axis of AEB and CDE is EX, since we proved that EX also lies on both circles. So that CF, AB, and EX concur. But AEBX is a rectangle. So this concurrency point should be the midpoint of AB. Does anyone have any questions up to this point? This first part is all geometric observations, and the second part will be the computation. Let's move on to the computation. Here it's helpful to just zoom in on triangle ABC and the points M and F. So we have so if we take a look, we know two of the three sides of ABC. We're given that AB should be 48 and BC should be 35. And we also know that if M is the midpoint of AB, and we extend CM to the circumcircle, and it intersects at F, then CF is 50. So let's just make a note of all the lengths we have right now. AM and BM are 24, BC is 35, and CF is 50. So here we can use power of a point M to get information about MF and MC. We know there's some, but we don't know what they are yet. However, we can use power of a point, which says that AM times BM is CM times FM. Now let's substitute this in. AM and BM are both 24. We'll let CM be our variable. And since CF is 50, we know that that FM is 50 minus CM. And this is a quadratic in CM. You can solve this quadratic or eyeball it if you want. And the solutions are CM are 18 and 32. Cool. So now we have triangle ABC. We know what two of the side lengths are, and we also know the length of a median, and we want to find the third side. And to do that, we can use the median length formula, which relates the length of a median with the lengths of the three sides. So in particular, 4 times CM squared should be 2BC squared plus 2AC squared minus AB squared. And we know what CM, AC, we know what CM, AB, and BC are. So we can rearrange this equation to solve for AC. And we have that AC squared is this fraction. And this is good. We know all of the numbers on the right-hand side. So we throw them in. BC is 35, AB is 48. The CM is either 18 or 32. And we throw it in, and again, we get the two possible values of AC. Yep, the median length formula is a special case of Stewart's. It's useful to remember separately, just because it's one of the most common uses of Stewart, and you can avoid plugging everything in when you just know the formula. And so we get these two possible values for for AC. Any questions about this problem? If not, then we can move on to our next problem. So the diagram and statement are as shown. I'll give you a bit of time to look over it. And again, the diagram on this first page is a clean one, but the second one will be filled. So it's good to get a clean diagram for yourself. Okay, let's start on this problem. This is the geometric steps for this problem are quite tricky. So let's try to start off by making some synthetic observations. So what synthetic observations can we make about this diagram on the front page? We have these three circles and they intersect or a tangent as shown. Yep, so good observation. So we have the radical axis of omega 1 and omega 2, which is PQ. And we introduced these new lines to handle it as shown. So before I had different explanation for why we drew these tangents, but I just realized that we can just straight use radical axis theorem on the three circles. The radical axis of omega 1 and omega 2 is PQ. The radical axis of omega and omega 1 is their common tangent at A. And the radical axis of omega and omega 2 is the radical axis at B, is the common tangent at B. And so by the radical axis theorem, they're going to concur at a point C. So a different explanation for this is if we let the tangent at A and the tangent at B meet at Z, then ZA equals ZB because they're both tangent to omega. But ZA squared is the power of Z with respect to the first circle. This is the definition of power, or by power of a point. And ZB squared is the power with respect to the second circle. So it has the same power with respect to the two circles, so it lies on PQ. But again, it's easier if you think of it as straight radical axis theorem on the three circles. The tangent at A, the tangent at B, and PQ are going to concur at a point C. So this looks pretty good for the picture right now. We can handle the tangencies and the common chord, but right here we're a bit stuck. We have AP, BP, and PQ, but it doesn't seem like we can do anything useful with them right now. Let's try to make another geometric observation. Does anyone have any guesses? In particular, given the diagram shown here, what other relationships are there between the points? Well, if we look at the diagram here, well, the points A and B are given. There's nothing we can say about just the points A and B. The point P is also a given. We just choose a point on A, B. But then, there is no structure to A and B or P, but afterwards, when we build up the diagram, there is structure to the remaining points. So the next point that we build is Q. Is there anything that we can say about the point Q in relation to the rest of the diagram? In particular, in this picture, with our new point z introduced, it seems that AQBZ is cyclic. That is those 4 points line of circle. Realizing this is quite tricky, I think the easiest way to do this would be through inversion, which is a quite advanced technique. But if we have a good eye, then we can verify this with some basic angle chasing. In particular, let's try to show that angles QAB and let's try to show that angles AQZ and ABZ are equal. Well, angle AQZ, which is angle AQP, is equal to angle BAZ because of the tangent line AZ. ZQA is PQA. We're just renaming the same angle. And this is equal to angle PAZ because ZA is tangent to omega 1. And now PAZ is equal to ZBA because triangle ZAB is isosceles. ZA and ZB are both tangent to omega, so they have to be equal. So now put this together, we see that ZQA and ZBA are equal, which confirms our suspicion that AZBQ is cyclic. Any questions? Let's move on with this problem then. So now that we know that AZBQ is cyclic, we get a lot more information. In particular, this circle ABZ actually also passes through O. We can see this because angle OAZ and OBZ are both 90 degrees because of the tangency. So the circle actually has diameter OZ. So since Q actually lies on the circle, we know that OQZ is 90 as well. What does this mean in particular? If we know that OQ is perpendicular to XY, what can we say about Q? So the foot of the perpendicular from O to XY is going to be the midpoint of XY. So now Q is the midpoint of chord XY. So after making this big observation, the computations for this problem are very quick. So now we know what AP, BP, PQ, and XY are. Not PQ, AP, BP, and XY. So now, since we have the midpoint condition, we know that XQ should be 11/2 as well as YQ. And PY is going to be 11/2 minus PQ. We're using PQ as a variable here because that's what we want to solve for. So let's take power of a point at P. We know that PA times PB is PX times PY. But we know that PA is 3, PB is 5, and then we just solved for PA and PB, which are PX and PY, which are 11/2 plus PQ and 11/2 minus PQ. And this, we can use difference of squares, and this immediately solves for PQ squared, which is 61/4. And answer your objection. So once we made the observation that Q was the midpoint of XY, the computation was really quite direct. Are there any questions? If not, then I hand it over to William.
Okay, so for our last few questions, we're going to be exploring a few stranger applications of radical axis and power of a point. So here's our first example. I'll give you a few moments to read it and feel free to type any suggestions in the chat. And sorry for the slightly cluttered diagram. We made it to scale. You might want to draw a slightly out of scale diagram on your paper to separate the points DM and EN a bit more. Has everyone finished reading the question? So does anybody have any initial observations about this diagram? They don't need to necessarily look helpful to finding the ratio. So I guess one thing to note off the bat is that line AP is a common chord of the two circles. So we have that APQ is a radical axis. This will be useful later on. But before we begin the question, we're actually going to prove a short lemma, which looks a bit strange, but is actually really useful. And it's called the linearity of power. So linearity of power states that if we have two circles, omega 1 and omega 2 in the plane, we can define a function f on all points in the plane, such that f of p is equal to the power with respect to omega 1 minus the power with respect to omega 2. And we claim that f is a linear function in p. So linear function sounds a bit strange because p ranges over r squared rather than r. But it's basically the same as a normal linear function. If we increment in a certain direction, no matter where we increment, the increment in f is always the same. So that's what linear means. In particular, if we take the weighted average of 2 points, the weighted average of their f values is equal to f of their weighted average. For example, like f of a plus f of b over 2 will be f of the midpoint. So this is what we want to show. And this is actually quite a straightforward application of coordinates, similar to how radical axis was originally proven. And there'll be a full solution inside the handout, but for now, let's just quickly breeze through it. If we let p be equal to xy and omega 1, omega 2 have radii r1, r2 and centers x1, y1, x2, y2, can anybody tell me what f of p is? Okay, so we can just plug in the numbers we have right now straight back into the formula for F. So we have power is equal to OP squared minus R squared. So in this case, it's going to be X minus X1 squared plus Y minus Y1 squared minus R1 squared. The first three terms denote the power with respect to omega 1. And then we subtract X minus X2 squared minus Y2 squared, and then add an R2 squared. And the last three terms refer to negative of the power with respect to omega 2. So now the thing to know about this equation is that the x squareds actually cancel out because we have a plus x squared, negative x squared. And the y squareds also cancel out. So the quadratic terms cancel out and f must be linear. So actually f of p is like ax plus by plus c for some constants a, b, and c. And it's clear from this that f satisfies the linear properties we want. So using this lemma, we can now begin to attack this question. So going back to the original question, how can we use linearity of power here? So first of all, linearity of power requires two circles. Which circles should these be? This should probably be pretty evident. Feel free to type in the chat. Yeah, the only two we've notated, ADE and AMN. So we define f of p to be the power with respect to ADE minus the power with respect to AMN. So are there any points for which we can find f very easily? Yeah, f of a is 0. In fact, yeah, but q is probably a bit more useful. F of q is also 0. And this is because any point on the radical axis satisfies that the two powers are equal, so they have to subtract the 0. So f of q is equal to 0. So now where should we apply linearity of power? In particular, we want to completely utilize the linear properties of the function f. Yeah, we want to consider b and c. So note that q is on line BC, which means that it's some weighted average of b and c. In particular, q is going to be equal to, okay, so we have that q is QC over CB along the way from C to B. So it can be expressed as a weighted average of QB times C plus QC times B all over BC. Does that make sense? It's a weighted average where like it's QC close to C and QB close to B. So we can think about it as like balancing a lever or something. So now that we have this, we already know that the right-hand side is 0. So if we set it to 0, multiply by BC, and then rearrange some terms, we just get that BQ over CQ is going to be negative f of B over f of C. So now we have a formula to find the ratio we want. So what's nice about this form? We actually can calculate f of B and f of C very easily. So if we want f of B, for example, we want to know the power of B with respect to ADE and the power of B with respect to AMN. So let's compute the quantities Bn and Be. So can we do that? Remember, ACB is a 13, 14, 15. Oh yeah, and just type in the chat if I'm going a bit too fast. Yeah, we can use angle bisector theorem to find BE. And Bn is easy, it's just because n is the midpoint. So Bn is going to be half of AB, which is 15 over 2. And BE we can compute using angle bisector theorem. It's 14 over 13 plus 14 times AB. And plugging in numbers as 70 over 9. So this means that f of p is going to be Bn I mean, it's going to be BE times BA minus BN times BA. And when we plug in all our numbers, we're going to get 25/6. So the rest is easy. We do the exact same thing with f of c. So CM is 13/2. CD by angle bisector theorem again is 182/29, which makes f of c equal to negative 169/58. So once we have these values, just remember that our ratio we wanted at the very beginning was negative f of b over f of c. We already have both f's, and when we plug in things, we should get 725/507, which makes our answer 218. So are there any questions on this question or the technique of linearity of power in general? Looks like no. So we're going to move on to our final question of the day, which is IMO 2009 question 2. So I'll give you guys a few minutes to read the question. And as usual, feel free to type any ideas in the chat. Okay, so let's get started with this question. The first thing to notice is that the condition we want to prove is quite strange. We want to prove that OP is equal to OQ. So does anybody have any ideas on how to show that these two lengths are equal? Feel free to type in the chat. Yep. So normally our instinct might be to prove that OPQ is isosceles, for example. But the angles OPQ and OQP are really ugly. And this idea will probably not work. Instead, as some people said in the chat, note that OP is equal to OQ means that P and Q have the same power with respect to circle ABC. This is because power of a point was defined to be the distance from O squared minus R squared. So if their distance is So if their powers are the same, their distances have to be the same. But P and Q actually have really nice representations of their power. In particular, the power of P is AP times PC, and the power of Q is AQ times QB. So it suffices to show that these two products are equal. And now this looks a lot simpler. So first of all, can we compute CP and BQ? Let's try to express CP and BQ using the lengths KM, ML, and KL. Remember, M, K, and L are all midpoints of their respective lines. Yep. So as we all pointed out in the chat, MK is a midline of triangle PQB, since its endpoints are midpoints of the respective sides. So BQ is just twice MK, and likewise PC is twice ML. So now we have expressions for BQ and PC. So we'll focus on AQ and AP. So to get these values, we probably want to use some angle conditions. So we haven't at all used the fact that KLM is the circle is tangent to PQ yet. So let's use this condition to get something about the angles. So let's try to apply some of the techniques from angle chasing in the first half of class. Feel free to type in the chat any partial progress you guys can get. Yep, that's a good idea. So from the chat, we have that angle AQP is equal to angle KMQ. This follows from the fact that MK and AQ are parallel because MK is a midline, and angle QMK is equal to angle MLK, but because QM is a tangent. So this follows from angle conditions given by tangent lines. So the angle chase is written in reverse on the bullet point. So this gives that angle MLK is equal to angle AQP. So now similarly, we can get angle MKL is equal to angle APQ. So combining these two angle conditions, we have that triangles APQ and MKL are similar. So what does this tell you about AQ and AP? So just from similarity ratios, we just get that AP over AQ is equal to MK over ML. So now we have relations involving AP, AQ, BQ, and CP. So we can now try to find the ratio of the powers of P and Q. In particular, AQ times QB over AP times PC is equal to ML over MK times 2MK over 2ML. The ML over MK comes from the first two, comes from AQ over AP, and the latter term comes from QB over PC. And the MLs cancel, the MKs cancel, and our answer is 1. So this means that AQ times QB is equal to AP times PC as desired. So the powers of P and Q are equal, and OP equals OQ. So are there any other questions about this question? Well, looks like no. So that concludes today's lesson on Advanced Geo. Thanks for everyone for coming, and we'll see you again next week.